Hello and welcome back. In today's talk, we're going to be looking at the differences between continuous wave Doppler ultrasound and pulsed wave Doppler ultrasound imaging. Now, both of these imaging modalities utilize the underlying principles of Doppler imaging that we looked at in our previous talk. And we saw there that the Doppler shift, the shift in frequencies that we measure on our transducer, is the difference between the frequency we are receiving within that transducer and the transmitted frequency that we propagated out into the tissues. Now, that Doppler shift can also be calculated using the Doppler equation. And the Doppler equation will determine how much Doppler shift we measure on that ultrasound transducer. We've seen that the higher the frequency we transmit into the tissues, the higher the Doppler shift will be returning back to our transducer. Also, the higher the velocity of the moving object that we're trying to measure, the higher the Doppler shift. Cosine theta also determines how much Doppler shift we're going to measure on our machine. Now, cosine theta, that value actually increases the smaller that Doppler angle, the smaller the theta angle gets. So the smaller our Doppler angle, the more Doppler shift we register on our machine. Now, often when we're looking at this equation, the unknown variable, the thing we're trying to calculate, is the velocity of the object moving within our image. So we can rearrange this formula to isolate velocity, to isolate the unknown value. And we can plug in all of these values, all of which we will know, to calculate the velocity of the object moving within our tissues. Now, way back at the beginning of this course, we looked at the principle of dampening and quality factor. And I said that a transducer crystal is much like a cymbal on a drum set. When you hit that cymbal on the drum set, it will resonate at a certain frequency, and it will resonate for a long period of time. Now, the frequency at which it resonates is due to the diameter of that cymbal. Much like a piezoelectric crystal within our ultrasound transducer, its resonance frequency is determined by the thickness of that piezoelectric material. Now, if we don't dampen that piezoelectric material, it will resonate for a long period of time at a set frequency. It'll have what's known as a narrow bandwidth. The frequencies within this ultrasound wave will be very close to the resonance frequency. There'll be a very narrow range between the lowest frequency and the highest frequency. It'll all be clustering around that resonance frequency. Now, the problem with this is this long spatial pulse length, or this continuous wave, allows no time for listening for returning echoes. So we said that this is really good for Doppler imaging because we get a pure frequency. And in Doppler imaging, what we're looking at is the differences in frequencies. We're not measuring the strength of the echoes returning back. We're measuring the Doppler shift coming back and using that Doppler shift value in order to calculate the velocity values. Now, when we looked at pulse echo ultrasonography, we saw that we needed to reduce that spatial pulse length in order to have this receive time, in order to register the returning echoes and plot them at a distance away from our ultrasound transducer. And we did this by dampening the piezoelectric material. That dampening material is much like a wet rag on top of this cymbal. It makes that note when we hit the cymbal short and have quite a wide range of frequencies. It's got a wide bandwidth, a low quality factor. But that wide bandwidth allowed us to have a short spatial pulse length, a really short, sharp pulse that went into the tissues, and then we could spend the rest of the time waiting for those echoes to return. And in pulse echo ultrasonography, we weren't really worried about the frequencies of the waves returning. We were worried about the timing of the waves returning. It was the time that we used to determine the depth of the various different reflectors within our tissues. And it's these two concepts that are really important to keep in the back of your mind when we're comparing continuous Doppler ultrasound imaging and pulse wave Doppler ultrasound imaging. So let's start by having a look at continuous ultrasound imaging. Now, in order to create a continuous ultrasound image, we need a minimum of two transducer elements. One to transmit the continuous wave into the tissues, and one to receive the returning echoes. It's not like pulse echo ultrasonography where we have a transmit time and that same crystal can then receive the echoes in the receive time. This transducer crystal here is continuously propagating an ultrasound wave into the tissue. There is no receive time for that same crystal to analyze the returning ultrasound frequencies. We need a separate crystal in order to do that. Now, what happens is we've got this high quality factor ultrasound continuous wave heading into the tissues. that is going to interact with moving objects within the tissues. In this example, we have a blood vessel here. The blood is moving towards the ultrasound transducer. Now, depending on the velocity of that blood, we will get ultrasound waves returning back to this ultrasound machine. And there will be no gaps in this ultrasound wave returning. It is a continuous wave coming in. We're getting continuous reflections coming back from this moving blood within this vessel. Now, those continuous waves heading back will have varying frequencies depending on the velocity of the blood. We know that when blood moves around the body, it doesn't move at a constant velocity. It moves faster in systole, it slows down during diastole, and in some vessels we can actually get reversal of blood flows for periods of the cardiac cycle. So depending on the velocity of that blood and the direction of that blood, the frequencies returning to our ultrasound probe will vary. Now, what we can do with these returning frequencies, or the returning Doppler shift, is use the Doppler equation to calculate the velocity of that blood at every given point within these returning echoes. So continuous wave ultrasound can't create an image by itself. We've got no receive time to then time the pulses coming back and then plot those varying distances, giving us an image. What we can do is continually sample those returning echoes with no break in between these receiving echoes that the ultrasound machine is measuring. So we've got a continuous stream of data coming back to our ultrasound machine. And the data that's coming back is the Doppler shift that is determined by the velocity of the blood within that vessel. Now, the Doppler shift frequencies actually fall within the audible part of the acoustic spectrum. If you cast your mind back to one of the first talks within this course, we saw the acoustic spectrum, and there was a range of frequencies there that are audible to us. These Doppler shift frequencies coming back are within that audible range. So although we can't create an image here, what we can create is a sound value for the returning echoes. And you may have used a continuous wave ultrasound when looking for viability in a limb, when you're worried about blood flow being blocked to the distal part of a limb. You may have placed that ultrasound transducer on the radial pulse and heard those Doppler shift frequencies coming back. And the higher the pitch of those frequencies, the faster the velocity of the blood within this blood vessel. Now, because we're not creating an image here, we can't measure this Doppler angle here, and we can't get actual velocity values back. Now, if we want to calculate actual velocity values while using continuous wave Doppler imaging, what we need to do is use duplex Doppler imaging. We have an ultrasound machine that is creating a B-mode image. That is a pulsed echo ultrasonography that is creating this B-mode image. Then, two crystals within that ultrasound transducer can act as continuous wave ultrasound probes. The other crystals that lie laterally to this are using pulse echo ultrasonography. These two crystals do exactly what we looked at in the previous slide, but now we can calculate our Doppler angle. And using that Doppler angle, we can get actual velocity values coming back. Now you can see that the area sampled by the continuous wave ultrasound transducer elements is a large area here. Everything within here, anything that's moving within this diamond shape, will be returned back to our receiving transducer element. So when we look at our B-mode image and we draw a line down where we want to calculate the velocities, we are calculating all the velocities in this area here, not just the vessel that we are interested in. And that's one of the downsides of continuous wave ultrasound imaging, because if we had two vessels within that sensitive area, we'll be getting data from both of those vessels coming back. And it'll be quite difficult to isolate a single vessel if we were just interested in the red vessel here. Now, blood could be going in one direction in our blue vessel and a different direction in the red vessel, and we would get the summation of those returning frequencies and wouldn't be able to isolate an individual vessel. Now, what happens if we want to isolate a specific vessel? Well, what we need then is our ability to measure depth within a tissue. Now, the only way that we can measure depth in a tissue is to have a receive time, to send a pulse out and wait a set period of time that will allow us to listen for those returning echoes, use that round trip time to calculate the distance within the tissue. That brings us to pulse echo ultrasonography, and this is the major difference between continuous and pulse echo ultrasonography. So again, we've looked at this principle. In order to calculate a depth within tissue, we need a pause, we need a receive time. we need to dampen the ultrasound beam that is heading into our tissue in order to create a shorter spatial pulse length and allow for that receive time coming back. Now in pulse echo ultrasonography, again, we create a beam mode image that has our vessel of interest. Now in order to create this beam mode image, we have an ultrasound transducer with an array of transducer elements that are sending out pulse echoes into the tissue, A line by A line at a time at a set frame rate, which we looked at when we looked at temporal resolution. Now what we can do is select an active area within this beam mode image. Now the beam mode elements that are responsible for creating the image within this active area are no longer listening for the strength of the returning echoes, the strength of the tissue boundaries, and creating a grayscale value. What they're listening for is the Doppler shift of the returning echoes. And depending on the Doppler shift of those returning echoes, instead of giving it a grayscale value, it will give it a color value. Now, if the Doppler shift is a positive value, i.e. the blood is flowing towards the transducer, it will give a color value in the red region. And the higher the Doppler shift, the more that value will turn towards this orange spectrum here. So we're getting a directional value here. If blood's flowing towards our transducer, we get values in the red scale. If blood's flowing away from our transducer, we get a negative Doppler shift value. We assign blue values in this active area. So there's a directional component here. Not only is there a directional component, there's a magnitude component. The higher the velocity, the more the Doppler shift, the brighter these colors will be, closer to orange than they are to red. And in the blue regions, the higher the velocity away from the transducer, the more light the blue values get. If there's no movement, no velocity, then we get black in the regions of this active area here. Now we don't have a set angle of inclination here. We can't actually calculate the exact velocity values, and that's why this is called color Doppler. We are assigning a specific color on a magnitude scale. Now when we are looking at a vessel, blood flow in a vessel, the center of that vessel generally has faster blood flowing. There's laminar flow within the middle of that artery, say. By the walls of the artery, we get slower, more turbulent flow. And so often in a color Doppler, you will see the center of the vessel being more orange and the peripheries of the vessel being more red. Now what if we want to know the specific velocity in a point on this vessel here? Then we need to use what is known as spectral pulse wave ultrasonography. Now on the outside of this active area, we are creating the image using these small spatial pulse lengths with receive time here. We've got a short pulse repetition period, we've got a high pulse repetition frequency. Within the active area, in the color Doppler mode area, what we need to do is increase our spatial pulse length a bit. We need to narrow that bandwidth down in order to get good frequency data coming back. Now because we've increased our spatial pulse length and we still need to wait for those echoes to return, what we've done is we've increased our pulse repetition period. Now the pulse repetition period is the same as the time it's taken to create an A line of data. And we've seen that in soft tissue, our pulse repetition period, or the time taken to create an A line of data, is equal to 13 microseconds times the depth that we are trying to image here. So this active area has a longer pulse repetition period. It takes longer to create that overlaid color Doppler ultrasound image. So our temporal resolution in this part of the image is going to be worse than the temporal resolution of the beam mode around here. And that's based on the differing pulse repetition periods. And we've seen that the pulse repetition period is inversely proportional to the pulse repetition frequency. The longer the pulse repetition period, the period of time from one pulse to the next pulse, the lower our pulse repetition frequency, the fewer times per second that we can create individual A lines within the image. And this is a really important concept to remember, especially when we start trying to calculate actual velocities within the blood vessel. So what happens now if we want to actually know the specific velocity of blood within the center of this vessel? We can no longer use color pulsed wave Doppler. What we now need to use is called spectral pulsed wave Doppler. Now in order to create a spectral pulse wave Doppler image, we take one line of ultrasound data within this image. We take a single A line crossing the vessel. Now we set this A line to intersect our vessel of interest. The second thing we do is set what's known as a gate. Now a gate is a region that we want to measure the velocity within this vessel. The region between these two lines is where we are measuring the velocity. We can increase the size of this gate or narrow the size of the gate. The more we increase, the more red blood cells flowing through that gate, the more velocity changes we'll see heading back to our ultrasound transducer. The narrower we make that gate, the more specific the velocities will be to that smaller region within our image, the narrower our spectral waveform will be. Now, the last thing that we need to set in order to be able to calculate an actual velocity value is the Doppler angle. We set this line on our ultrasound machine to match with the direction of the vessel. And we've seen that angle correction, accurate angle correction, is really important for accurate velocity measurements. Now that we've set these three parameters, the A line, the gate, and our Doppler angle, we can calculate the velocity heading through this particular region in our image. And because we are sending multiple pulses over a period of time, our pulse repetition frequency, we can then calculate or plot those velocities over a period of time. And this is what gives us a spectral waveform. Now, in the next talk, we're going to look specifically at spectral waveforms and break down the various different values here. But for now, the y-axis on our spectral waveform indicates the velocity of the blood within that vessel. The x-axis represents time. As time goes, what is the changing velocity over time? Now we can see that as the heart contracts during systole, we get an increase of velocity flowing through that vessel. We then have blood flowing still in the same direction over diastole until the next contraction of the heart here. And as I say, we're going to break this down further in the next talk. Now cast your mind back to when we were looking at the continuous wave Doppler. We saw that the returning ultrasound echoes were continuous. There was no break in the sampling of those returning echoes. And we got the exact frequency shift over time because it was continuously returning back. Now in pulse wave Doppler, we are sending short pulses into the tissue and then waiting for those pulses to return back. And we're only measuring the frequency shift of those returning pulses. There are periods of time when we are not, in fact, sampling the actual velocity within this vessel. And if we want to plot these velocities over a period of time and we want to accurately measure the frequency shift, we need to sample as regularly as possible in order to accurately measure. Now, it goes without saying, because we are sampling at a set rate, there's a maximum velocity that we are actually going to be able to accurately calculate. And this is what's known as the maximum Doppler shift within the tissues. Now, if you have a look at this graph here, you can see that we've got returning frequencies coming back towards our ultrasound machine. Now, this frequency that is returning is representative of the Doppler shift we are measuring. Each one of these black lines represents the sampling period, our pulse repetition frequency. How often are we getting returning echoes from the gate that we have mapped out? Now, if our pulse repetition frequency samples that returning Doppler shift frequently enough, we will be able to accurately measure the frequency of that returning Doppler shift. Now, there will come a limit when we can no longer accurately measure the returning Doppler shift frequency, and that's what's known as the Nyquist limit. Now, the Nyquist limit states that we need to sample a returning wave, a returning Doppler shift frequency, at least twice within one wavelength. So if we have a look at this wavelength returning, and we take two consecutive points on that wavelength, we take the peak here and the peak here, we can see that we've sampled once, sampled twice before the next wavelength starts. We will be able to accurately assess the frequency here. If we take this peak here and look at the next peak, one wavelength in this returning ultrasound, we see that we've only sampled this wavelength once. And if we only take 1 point on a wavelength, we haven't got 2 points to join. We can no longer accurately represent that frequency returning. The frequency that the machine thinks is coming back here will be way lower than the actual frequency coming back. And ultimately, the velocity that we calculate will be wrong. So our pulse repetition frequency determines the maximum Doppler shift that we can detect. And we can use this equation, the Nyquist limit, to determine that maximum Doppler shift that we are able to detect. The maximum Doppler shift we can detect is half the pulse repetition frequency. We need to repeat that pulse twice within one wavelength here. Now we can use this equation and plug it into our velocity equation. The maximum velocity that we can calculate is determined by the maximum Doppler shift frequency. So we can plug that maximum Doppler shift frequency into our Doppler equation here. And because we have a PRF value, we can then substitute the PRF value into the Doppler equation. Now you can see here that the higher the pulse repetition frequency, the more we are sampling per second within our tissue, the higher the velocity we are able to measure within our tissues. We can also see that the frequency of the ultrasound transducer that we're using plays a role in the maximum velocity that we can calculate. The lower the frequency of our transducer, the lower the Doppler shift that will be returning to the transducer. The velocity of the blood in the vessel hasn't changed, but the amount of Doppler shift has changed based on the incoming frequency that we've sent from the transducer, and then that Doppler shift heading back will be slightly less. We then don't need to sample that Doppler frequency as much for the same velocity, allowing us with a lower frequency transducer to detect higher velocities within our pulse wave Doppler. Now we've seen that the pulse repetition frequency is the inverse of our pulse repetition period. Now we set our pulse repetition period depending on how deep in the tissue we want to image. The deeper we're trying to measure within the tissue, the longer that receive time has to be. Therefore, the longer our pulse repetition period has to be. And the longer that pulse repetition period, the fewer times per second we can sample the tissue, the lower our pulse repetition frequency. So the deeper this vessel is within the tissue, the lower our pulse repetition frequency can be, the lower the maximum amount of Doppler shift that we can measure. And ultimately, the maximum velocity of blood that we're able to measure decreases the deeper we go into tissues. So you can see that continuous wave ultrasound imaging has various positives. It is continuously sampling the frequencies returning, so we can pick up much higher velocities. Although we can't actually create a specific image with a continuous wave Doppler ultrasound image, we can't create these color active areas within a B mode image. We also have a larger active area within the continuous wave Doppler ultrasound imaging. We can't select a specific depth. Pulse wave Doppler has various advantages. We can superimpose color images over a background B mode image. We can select specific depths and specific regions on our image to measure specific velocities. But because we are waiting for those returning echoes in order to accurately plot those, we can only measure up to a certain maximum velocity. And there will be periods of time when we need to change over to continuous wave Doppler in order to measure those higher frequencies. Now in this talk we've looked at color pulse wave Doppler and we've looked at spectral pulse wave Doppler. And I just want to end off by showing you the last type known as power pulse wave Doppler. Now power pulse wave Doppler doesn't take into account direction. Both spectral and color Doppler take into account which direction the blood is traveling. Power pulse wave Doppler only takes into account the magnitude of the frequency shift heading back towards our ultrasound probe. And depending on the magnitude, it will plot a red to orange value here. So blood traveling away from the transducer at a specific velocity and blood traveling towards the transducer at a specific velocity will have the same color scale on a power mode Doppler. It's insensitive to direction. And because it's insensitive to direction, we don't need to set a set Doppler angle. And power mode Doppler is really good for picking up low flow within a tissue. If we're looking at a specific mass within an ultrasound image and all we want to know is there flow of blood within that mass, we can use power mode Doppler to pick up low flow states as well as deeper structures where we can't measure high velocities within the tissue. So we have power Doppler, color Doppler, and spectral Doppler. And any time where we use these pulse wave Dopplers and superimpose it on top of a B mode image, that's what's known as duplex Doppler imaging. Now we've looked briefly at spectral Doppler imaging, and there's a lot of information that we can get from these spectral pulses that we plot on this graph here. In the next talk, we're going to be looking at various different types of spectral waveforms and how we can use them clinically in order to determine blood flow within a vessel. After that, we're going to look at what happens when we reach that maximum velocity in our pulse Doppler imaging. And we'll get a phenomenon known as aliasing, which is an artifact within pulse wave Doppler imaging. And in that talk, we'll look at various mechanisms that we can use in order to reduce aliasing within our spectral pulse wave Doppler imaging. So I hope that helps. Knowing the difference between continuous and pulsed wave ultrasound and knowing the benefits and drawbacks of each is really important when it comes to ultrasound physics exams. And if you're studying for a physics exam, I've linked a question bank below where we go through some questions that look at the differences between continuous and pulsed wave imaging. So if that's you, go check it out in the first line of the description. Otherwise, I'll see you in the next talk. Goodbye, everybody.